renewable energy sources. So that's among this, the solar is considered among the most cheapest and is the available. So that's why today's topic is mainly focused on the development of the solar energy consumption, is the production of energy from solar, and then that's the drive from use of the solar energy we can produce different type of energy, and that can be converted for our future expected. And also we can focus on this, how can we store this energy in this future. So this among the limited, so that's why we can consider this among the limited methods of solar energy conversion and utilization. Solar water splitting has been considered as the most effective and cleanest way to produce the another most renewable cleaner energy we can consider, that's the hydrogen. The hydrogen produced can then be used by the fuel cells to generate electricity, where the water constitutes the only emission. Starting from solar energy conversion and ending with hydrogen utilization, a renewable energy-based economic would be proposed and successfully structured in the coming decade. In order for solar energy to be the major contributor to the generation of clean fuel, that is the hydrogen energy, the efficiency of solar water splitting devices need to be improved. Technology for high capacity hydrogen storage, high performance fuel cell must also be developed in order to hydrogen to become the primary fuel for future renewable energy based economy. Throughout the human history, the advance in civilization have been associated with the discovery, development, and use of new materials. In many respects, materials can be considered as the parents of almost all technologies, as most technology breakthrough have been achieved through the development of new materials. Nanomaterials are beginning to play the important role creating new fields of science and new nanotechnology. In order to achieve technology breakthrough in effective renewable energy conversion, storage, and utilization, we need smart nanomaterials to fully develop the potential and renewable energy. To this end, the potential capabilities of nanomaterials must be extensively discovered at the more fundamental level. In this particular discussion, we provide a brief overview of nanomaterial design for selective technology and renewable energy conversion and utilization based on the research activities of clean energy engineering laboratory. Particularly, the topic includes the photoelectrochemically water splitting, photocatalytic hydrogen production, and others. We hope that this concept of nanomaterial design will offer a new paradigm to realizing the renewable energy based in the not so distant future. So that's why I welcome our first panelist, Dr. Subhashish Roy, to present his thought on this topic. Dr. Subhashish Roy, please.
May I start?
Yes.
Okay, very good afternoon to all of you. First of all, I would like to thank the chairman, sir, Durgapur local chapter, Mr. Sofikul Islam, sir, also the chairman, sir, Reddy, sir, for giving me opportunity to present my research work in this particular special webinar. So today I'll discuss the functional nanomaterials for energy and environmental applications. Am I audible properly?
Yes, you are audible.
Yeah. Okay. So today I'll discuss the functional nanomaterials for energy and environmental applications. Particularly nowadays, the perovskite materials that structure, these types of materials is very important because of its unique properties. So particularly in my labs, I used to synthesize different types of the perovskite materials and applied these materials to the different types of the energy, resource energy device purpose. So here I will discuss in this lecture, first the introductions of nanotechnology and the synthesis of the perovskite type materials and its behavior, and its applications of the different types of the energy oriented field like fuel cells, perovskite solar cells, photoelectrochemical water splitting, and low power consumption memory device like composite materials. So here in my labs, I used to synthesize different types of nano-dimensional structure like 1D, 2D, 3D, and that may be a composite or single perovskite structures. And these types of the defined nanostructures like nanospheres, nanofibers, holospheres, nanorod, these types of the materials and composite, we used to apply these types of the energy devices. And we used to make the prototype device for commercial purpose. So here, if you see the first, the multi-threading memory device, actually in the memory of our computer device, when it reads, it consumes huge amount of energy. So if we replace the memory device with the low power consumption materials like perovskite, TiO3 like that, then the power consumption of the computer device will be very less. So one of the applications of these perovskite materials to apply these materials as a memory device, as a multi-threaded state memory element. And next, we used to work in the perovskite solar cells. Nowadays, the perovskite solar cell reach around 28% efficiency, quite nearly close to the silicon solar cells. But few problems are still there to commercialize these perovskite solar cells. One is stability and the cost, and it's have the lead, that is poisonous element fuel. So we have to replace this poisonous element for making it environmental friendly. So these types of challenges still are there, in perovskite. So we work this synthesis of different types of the perovskite materials and apply and integrate the solar cells for the environmental friendly. And another field, we used to work in the water splitting systems. As we know, the electrode, photoelectrode, when it absorbs the photon, then it's produces the electricity. And that electron, produced electron, we can use to split the water and produce the hydrogens without giving any external source of energy. So these types of perovskite material we can use as a photoelectrode, and it can be easily split the water and produce the hydrogens. Though defined many drawbacks, still there are challenges we need to overcome here. And finally, we used to fabricate the polymer electrolyte membrane fuel cells, different types of challenges like hydrophobic property, because water accumulates in the systems of the proton exchange membrane fuel cells, which deteriorate the efficiency of the proton exchange membrane fuel cells. So these types of the perovskite materials may improve the water management problem inside the polymer electrolyte fuel cells. So we used to work on this also. So here, as we know, the nanotechnology is very important nowadays because it adds the very unique properties in the material. What types? Because when we apply this nanomaterials, if you see the environmental available nanomaterials, naturally available nanomaterials, we can copy the natural nanomaterials. Then it can apply in the laboratory scales at the artificial nano device fabrications. So here, why nanomaterials is important? If you see the particle size when decreases the nanoscale level, the surface atom ratio, it's huge increase, and also the surface atom number is quite huge at the range of the nanoscale level. Due to that, it's giving the different types of unique property, extraordinary property creates in the nanoscale level. So our target to make these different types of nano-dimensional materials and make this apply these unique properties for these particular applications on the energy field. So here, if you see the nanoscale level, we used to establish the size-dependent properties and define as the surface volume ratio we used to tune for the particular applications purpose. And finally we go to the quantum chemistry levels where we analyze with DFT all those theoretical structural properties correlations. So at the synthesis of these nanomaterials, we used to approach two types of synthesis process. Top-down fabrications process, where you start from the large materials and bring it down to the nanoscale levels. And another is bottom-up fabrication process, where we start from the individual atoms and build upward to the make a nanostructure level. Both are having some advantage and disadvantage. So these two processes we used to apply for making the nanomaterials. So now I will discuss the photoelectrode, which we prepare the synthesis in the labs for the photoelectrochemical water splitting. So if you see these systems, there is two electrodes there one is photoelectrode and another is counter electrode. So here, if we apply the voltage 1.23 around volt, then 1 mole of water will be split and produce 1 mole of hydrogens. So our target is making one photoelectrode which will produce itself the electron with effect of the photon, light only. And that 1.23 electron volt will not be required for splitting the water, much less volt, or without applying the voltage, we can split the water. So we have to increase the photon absorption property in the photoanode sections. So here most, if you check the literature, most of the materials actually used to be, that is maximum usable materials is hematite material. But there is a lot of challenges still there in the hematite. We have to modify the hematite and doping, or by using other material doping and also changing the surface property, we can tune this hematite material for these applications of these water splitting devices. So our objective is to develop the high efficiency solar to hydrogen ratio conversions, where we can get the hydrogens, amount of hydrogen giving input. So here are stable to in aqueous solutions. Particularly in the perovskite materials, we can easily tune these perovskite materials, and these materials without compromising this absorption property, its band gap tune extraordinary. We can tune, and also by tuning this, we absorb the huge amount of solar spectra for the applications of the water splitting system. So here, if you see the systems here, the battery were used is required to 1.23 volt battery to split the hydrogens and oxygen. Minimum voltage that required volt. Cathode charge and anode become when we fabricate this device for water. On the anode side, these two oxidized in presence of the photon catalyst, then hydrogen and oxygen in presence of the electrolyte, and finally produce the hydrogen and oxygen by applying the photon. So what are the challenges still now there? Particularly here, the band gap of this material is very important, because the photon absorption energy should be enough to split, to jump the electrons from the valence to conduction bands. So that's why the selections of the material which having very low band gap and tuning of the band gap, and which having the low recombination property, that material should be used for this purpose of the water splitting. So here, the sum of the properties, that is photocatalyst is required. One is the band gap, another is the high crystallinity defect, because defect create the recombination state. That means hole and electron combine in the recombination part, which will reduce the amount of the produced electricity. So high crystallinity required, where the defect free surface will be there, and long-term stability. Nowadays, the perovskite material is not stable. It is actually 1 or 2 days is deteriorates because of the molecular motions of the cation. So that's why the long-term stability is more important to transfer and use the water splitting, and not should be corroded. So here the benchmark is, in the hematite case, the conversion efficiency around the 10% required for the commercialized these devices, water splitting. And the current density should be around 10 to 15 milliampere per centimeter square. And it should be durable 1 or 2 years. So this benchmark we have to reach to getting its commercialized for these devices. So here in the challenges in the systems, one is the strong optical absorption materials we have to select. High electron mobility should be there, long lifetime of the charge carrier, stability, good catalytic property, and cost. When we select a material, these things, this property, we have to remember that the material should introduce these types of the property to reach the benchmark of this conversions efficiency. So here, if you see, when we fabricate the photoelectrode, there are the lot of the parameter dependence each other. The photon, energy, and environment both are correlated. And if you see this triangular diagram, there is the crystal growth, different types of the size of the crystal phase, shapes, bulk doping, surface doping, chemical state of dopings, and then interface atomic structure, all are correlated to each other. So when we're making the photoelectrode, then we have to optimize this doping, heterostructure, and crystal growth all together. And then we optimized and get this high performance photoelectrode materials. So for these different types of the, if you see the periodic table, there are different types of materials available, but some of the having advantage, disadvantage both in this material. In the practical case, no practical photon electron conversion device is produced till now because of the drawback of the some challenges still. So here our target to make the hematite material with band gap 2.1 electron volt around, so that it can absorb the visible spectra photon. And then theoretical conversion efficiency, it's already reported that 12.9. So our target to reach nearly close of that. What are the challenges? Are there challenges? Small charge transport, low hydrogen evolution reaction state, and low visible light absorption spectra. So those challenges we have to overcome by applying this hematite with tuning the band structure, structural morphology, and making the relations of the structure property. So for these commercializations, if you see the curve in ideal hematite photoanode, it can reach around 12 milliampere per centimeter square current density, and the voltage, minimum voltage required 0.4. But still now, current state, we are standing here, where the current density is around 4 milliampere per centimeter square, and still now the required voltage required around 1 volt around. So our target to improve this current density as well as the required voltage, minimum requirement voltage. So for this case, so increase the current density, we observe from the theoretical analysis that the morphology tuning can improve the current density of the hematite material. So we tune different types of the morphological structures, then apply it and check the current density, what about the current density we are getting. And then after reaching this current density, then our target to get the requirement voltage as minimum as possible. So for this case, the surface chemistry and catalysis is very important. The surface state, if we coat with the different photoresponse materials on the surface, like perovskite material, then the surface chemistry will be changed, and then photoabsorption property will be very high. Then minimum requirement of voltage will be also less, and it will reach to the theoretical values around 0.4 volt. So in this case, our first attempt to enhance the electrical conductivity, then band gap tuning modifications, then improve the crystallinity, then increase the carrier density of the space charge. For these reasons, we tune these morphological structures and the electrical property by doping the cobalt dope inside the hematite material. And then for the surface morphology, surface changing, we coat with the different types of the perovskite material on the surface, particularly lead halide material, which is nowadays very important material for any photoresponse properties. So this is the process how we fabricate this photo anode system from the FTO, fluorine doped tin oxide. We coated these materials on the tops of the TiO2 surface. Then hematite materials will be deposited. Then cobalt doped on hematite material with different types of the cobalt doped material we deposited, and finally we checked the properties of the electrical and electrical and optical properties. And this is the process we used to use, the spin coating process, where the sol gel process we produce different types of sol with different percentage of the cobalt doped, and finally we fabricate these two types of the electrode and these two types of the photoelectrode coating with the different types of the photoresponse material like PBTIU, ST, MA, PBI3 nanomaterial on the top. Then finally we check the photoresponse property. So here different types of the instrument we used as for characterizations techniques like AFM, XRD. In the XRD case, which analyzes the crystal structures of the strain properties and also the count of diffusion inside the matrix of the other hematite surface. Those things we analysis from this. And then from EDAX, elemental morphological confirmations we have done. The presence of the all element is properly and equity checks. Then the surface roughness we have checked from the EFM analysis, and surface roughness is quietly smooth. And then finally these materials would apply check for this optical property measurement check, where we check the absorption phenomena, where absorption properties, where different types of the cobalt doped we have done, then optimized where which percentage of the cobalt give the maximum absorption property, and that amount of the cobalt we use for fabricate the fabricate the photoelectrode. So here we have seen in the band gap, after checking this band gap, that 3% cobalt doped is giving the minimum band gap around 1.96 electron volt. So we fixed after optimize this band gap properties that the 3% cobalt doped with hematite will be used for this photoanode for getting maximum absorption. And this is the setup where we have done by using the AutoLab system, cyclic voltammetry or other all instrument systems. And this is the 3 electrode setups, counter and working electrode is still there. And then finally we checked analysis its properties. So before that, another we have checked that 3% cobalt doped is giving the maximum efficiency, maximum absorption or not. That's why we have done the degradation property with methyl orange. And here also we got that the 3% cobalt doped is giving the maximum degradations of the wastewater in the within presence of the photon response. So it's concluded that the 3% cobalt doped is giving the maximum absorption with presence of the photon response. And here also we have studied the degradations property mechanisms of these 3% cobalt doped hematite materials. And then we have checked the kinetic properties, kinetic behavior, where the kinetic rate of the kinetic is maximum in case of the 3% cobalt doped. Then we fabricate the photoelectrode. Then we check the photoelectrode properties. The anodic photocurrent reach around 3.4 milliampere per centimeter square as in case of the 3% cobalt doped. It was between the balance between the donor density, light absorption property, and surface roughness, all will require to optimize in this case. So here, if you see the efficiency value reach around the 1.72% around, but without coating on the surface of the photon response materials. For these reasons, just only 1.72 fold, we check the stability of this material. Then after 5 hours, still the stability of the material still remain the same. It is not the changes. So more or less, these materials is stable at around 5 hours. Then we check the Ferrotic efficiency. In case of the Ferrotic efficiency, we got the 95% around, 5% mismatch Ferrotic efficiency we got due to the some sampling error in this case. So here, if you see in the literature with 3% cobalt doped hematite, we stand here in case of the anodic photocurrent amount of property, that is 3.5 milliampere per centimeter square. So we have to reach beyond that to get as commercialized for these devices. So for this reason, we coated these two materials, perovskite materials, on the top of these hematite materials for getting the much more current density in this case. So here, if you see first fabrications of the perovskite materials, we check the XRD property for giving the proper phase formations happen or not, or there any impurities is there, that all those things we have checked. Then we also check the size of the materials, and we tune the size of the material by changing the temperatures or other parameters here. Then AFM analysis we have done for getting the surface analysis. Then finally optical from analysis we got the band gap value around 1.6 in case of the methylamine lead iodide. That is much better than the reported value, close to the reported value. So if you see these things, this photo anode is maybe used as for solar cells also. So in case of the solar cells, we first checked without putting in the water. This is how much solar cells efficiency it is giving in case of the photoanode sections. So here, if you see in the middle, that is the cobalt doped hematite material in case of the middle. In the bottom is FTO, fluorine doped tin oxide. In the top of this fluorine doped tin oxide, that is the buffer layer TiO2, and the upper top layer, that is the particularly perovskite material. Then the top, there will be the whole transport material. Then there will be the contact of the Ag or silver paste or contact will be there. So here, after fabricating this solar cell, that is the top contact and that is the bottom contact. From here, we design the band and diagram. Then finally, we check the efficiency of the material. Then we check the efficiency of these solar cells around, we are getting 4.3% efficiency in case of the 3% cobalt dome. That means it can act as a solar cells also, or it can act as a photoanode also. Then we applied this material for taking the stability duration study, where we more or less get the 5 hours is still stable, because in case of the perovskite material, after half an hour, the cationic site, particularly methylamine, that degrade, that come to the systems of the structures, and that is the problem creating the deterioration, the structure or degradations of this. That is the reason of the degradations of the perovskite materials. So in that case, here we got the stability around the 5 hours. Then we check the amount of the hydrogens we produced. In this case, here we have checked that 95% around efficiency we got in case of the 3% cobalt doped hematite coated with methylamine lead iodide. So finally here applied bias and photocarbon response we reach around 2.04, whereas it was initially 1.8. Then after coating with this perovskite material, it reached around 2.04% efficiency. So, and then we check the solar to hydrogen's efficiency. That is around, we got methylamine lead iodide 2.46 solar to hydrogen conversion efficiency. Here we got. So in this case, if you see this diagram, here theoretical conversions in case of the cobalt doped hematite methylamine, solar to hydrogen ratios and photon to absorption ratio, it should be reached around the 12.9%, but still now we are struggling, where we reach around the 2.5% efficiency. So still something, some of the parameter we need to optimize to reach the theoretical value. So here, if you see this video, so if you see in presence of the light, here in the photoanode, there is a producing the hydrogens, and we store these hydrogens in here in the another sections, and this is the counter electrode, that is the platinum electrode, and here we store and we measure the amount of the hydrogen stores in these sections, in the how long time, how much hydrogen we store, putting this light only. So this is our attempt to make a device fabrications, water splitting device fabrications in presence of the hematite with doping and structural tuning to get the maximum efficiency, solar to hydrogen efficiency, and photon absorption efficiency. So in this case here, still now we some of the challenges are there. like organic halide nanostructures that coated in the photoanode. Overall efficiency we reach 2.46 is must be should be more high for this for the commercialization of these devices. And the significant important improvement of the state of arts, the hematite photoanode, that the enhancements of the transport in the film by decreasing over the potential of the surface treatment. And the degradation, also the degradations, it is much more stable than the compared to literature. Okay. So here in this hematite photoanode, our next plan to improve the efficiency, which can reach the reach the theoretical value for these commercializations, and the stability must be more with replacing this other halogen material like iodine, bromine, and the optimization the necessary thickness, which can tune and give by tuning the thickness, absorption property, charge transport much may be improved. And lights should be maintained around the solar radiations, solar constants. And the controlling, we check the controlling temperature fluctuations of the active controlling system. These are the more the future target of this photoanode, making the photoanode. So here I conclude in here to fabricate the photoanode systems for the perovskite materials, and our DS fabrication still now is progressing, not yet completed still now. So then how much time I left? I have.
You can continue.
Okay, so this material, this perovskite, it is very important for various types of the purpose of applications. We also tried these perovskite materials in ferroelectric, magnetoelectric, and multiferroic. All these ferroelectric, all these properties we can get from these perovskite materials. So for this, particularly multiferroic memory, multiferroic devices, that shows both of the magnetic properties and ferroelectric properties combined in a phase. So here we synthesis different types of perovskite materials for the applications of these multiferric memory devices. So if you see in the literature, the single perovskite materials is having very low magnetoelectric power consumption coefficients. So it cannot be commercialized for the applications purpose. So for these reasons, we used to prepare the composite material where the magnetoelectric coefficients we can enhance by tuning the structural morphology. So if you see the different type of structural morphology, there is different type of structure like 1, 3, 2, 2, 0, 3 types of the structure, particularly composite type of structure. So in all the cases, if you see the 0, 3 types of the structural, in a particular like structural, where the piezoelectric matrix will be distributed with the other nanoscale matrix, and then it will be giving the maximum magnetoelectric coefficients here. So we use here the 0,3 types of the structural material for the applications of the memory devices for this perovskite material. So here we select as a piezoelectric material lanthanum doped lead titanate, which is having the much piezoelectric coefficients higher than the other materials. And for the ferromagnetic phase, cobalt iron oxide, which having the magnetostriction coefficients is very high, we used as a magnetic material. Then we make it is 0,3 types of the particular composite types. Then we structural tuning, we have done different types of more optimization process of the solvent precursor chemistry, flame deposition parameter, heat treatment, all those things is optimized. And then we check the magnetoelectric coefficients. Here we use the Sol-gel synthesis process for making the magnetic material, magnetic salts, and also the piezoelectric salts, lead acetate, dihydrate, and finally lanthanum modified lead titanate, and also the cobalt iron oxide. Then finally we mixed these two salts in the different compositions of the cobalt iron oxide in matrix of the PLT15, and then finally we optimized this doping percentage where we get the maximum magnetostriction coefficients. So if you see the structural morphology of this cobalt CO4 doped PLT15 matrix, here if you see some interesting point where after a certain percentage of the cobalt or CFO, there is a shifting of the peak. That means there is a diffusion of the cobalt inside of the PLT15 matrix. So it's giving some very important phenomena in case of the multiferric thin films. So here we check the same analysis where confirmed by the elemental analysis that the cobalt iron oxide and PLT, lanthanum, lead, titanium all are present here on the matrix. Then if you see the thickness, because of the ferroelectric property, the thickness measurement is very important to get the ferroelectric properties parameter, all those things. So if you see the thickness, the all are thickness more or less same in case of the all samples. So here finally, we measure the optical properties and electrical properties of the solid state thin films of the multiferric memory devices with different instrument after coating on the surface of the sputter. Then if you see the dielectric property on the of this material, after a certain percentage of the cobalt, the dielectric material increase and then it is decreasing with increasing of the cobalt iron oxide. Then it's give the important phenomena about the leakage of this cobalt iron oxide inside the PLT15 matrix. So we have proved one model that is diffusion of the cobalt iron oxide in case of the PLT15 matrix, where these percolations happen at the percentage of the 3% cobalt doping. If you see the increase of the thickness of the here, after here, when we reach to the 5%, there is a diffusion of the cobalt inside the matrix of this PLT15. So there leakage started in that case. So we have to stay before that where the leakage stopped. So here we define types of the variation of the real part dielectric constant applied frequency we checked. Finally, we check the ferroelectric properties, where if you see the 3.4% cobalt iron oxide is giving maximum polarization value, or it shows the maximum ferroelectric property. Otherwise, we have proved that the butterfly loops capacitors per voltage, where also shows the 4% cobalt iron oxide doping with PLT15 matrix, giving the maximum capacitance value. And here also different types of the model we have produced in the barrier height, all those things, electrical phenomena we have checked. And then we studied the magnetic properties of this material. And then we got the around increasing the cobalt iron oxide in case of the PLT15, the cobalt iron oxide increasing the magnetic property, also saturation magnetizations, all other values increasing or increasing of the cobalt iron oxide. So here, if you see the magnetoelectric properties in the PLT15, there are the lot of the different types of the zone is showing different types of the situations of the atom positions of these ferroelectric properties. So if you see finally this material, we have take the magnetostatic coefficients, which is very important for the applications of the memory device. If magnetostatic coefficients is very high, that means we can tune this material by applying this voltage or current. It is correlated with the magnetic and electrical property. That means if you put the electrical property is giving the high magnetic value, or if you apply the magnetic property, it is giving the high electrical value. That means power consumption of the memory device is very less. So here we conclude that we got the 250 around millivolt centimeter roasted electric magnetostatic coefficient, that is very high, and it can be usable for this optical disk for this memory device, which consume the much less power. So here we produced one prototype ferroelectric device. Actually, when you measure the ferroelectric phenomena, the instrument available, it is very costly. So in the lab scale, we produce these ferroelectric measurement systems in very less, around 10,000, which is in the where then when we measure in the outside, the instrument cost is very high, around 10 to 12 lakhs. So here, if you see this circuit, shower tower circuit, we follow this shower tower circuit and our DAC card with the lab view. we interface this computer with this thin film setup systems, and finally we check this ferroelectric properties of this material. If you see these LabVIEW programs on the top part is giving the output voltage of these ferroelectric loops, and bottom part it's giving that the output input voltage of this put. This is the front panel. If you start these systems and save this card with our sample, it is showing what types of the ferroelectric loops it is giving there. So if you save, this is the output voltage which is giving, and this is the input voltage we are giving in the circuit. So in our sample, it is giving this quite smooth ferroelectric loops is there. So by this way, with this hour circuit, very low cost device we can fabricate in the lab scale, and we need not to purchase the high costly instrument around 10 to 12 lakhs. So in the next, I'll discuss how to fabricate the solar cells without compromise, without the lead. Actually, the perovskite solar cells, what is the perovskite solar cells? So the most important factor is the lead introduced here, because lead is hazardous and it is not environmental friendly. So our target to minimize the amount of the lead with introduction of the other material environmental friendly like SN or cesium or other material, so that it can be environmental friendly. So if you see these fabrications of the solar cells perovskite material, this is our fabrications process, where in the middle the PIN or NPI, both systematic solar cells we used to fabricate. Here if you see the top contact is AU and the bottom is FTO, then whole transport material is there. That means it is N type, and perovskite materials that is produce the electron holes, and in the below that TiO2 there. So this is the fabrication system process we used to follow for making these solar cells, and this is the layer by layer structures of the perovskite solar cells for making the high efficiency. So in nowadays, if you see in the literature, it's reach around a 25.2 in case of the perovskite solar cells, but some of the drawbacks is still there. What drawbacks? Particularly, it's not stable, and the lead is very hazardous, and the cost. These three factors is challenges nowadays. If you overcome these three factors, then it can be easily commercialized. So in that case, lots of the parameter also here intercorrelated to each other, like the stability degradation, validations of the efficiency, and the manufacturing process, all are correlated to each other. So before making this one, if you see this card here, suddenly there in the tandem solar cells, Germany recently reported that they got around a 29.8% efficiency, that quite close to the silicon solar cells, but it is very costly as it is tandem solar cells. So our target, fabricate these solar cells. This is solar cells with methylamine lead iodide, replacing the lead particularly in the positions with SN, with different types of doping of the SNs. And these fabrications of the cells, if you see this FTO glasses on the tops, then spin coating, then finally after spin coating drying, we got this. This is the silver paste coating, and this is these types of the cell we used to prepare here. Then finally, we check the morphology property and XRD characterizations for confirmations, the purity of phase formations of the behavior of the cell. And then we have observed different types of the tune percentage. When we tune, then different types of the morphology we are getting, like nanorod, nanosphere, all those things. So we optimize this morphology after checking this electrical property of the cells. Then here we got around 3.84 20% SN doping, which is maximum in case of the here. So here we can conclude that the 20% SN doped is giving the maximum efficiency, and we can replace the lead around 20%, and beyond that the efficiency is decreasing. So finally, I just last discussion about the fuel cells. Fuel cells is having the problems of water management problems because it's as a site molecules water produced and accumulated on the surface of the electrode. So we try to overcome this water management problem. So making is hydrophobic materials on the tops of this one of the electrodes. So those are the challenges still now in the fuel cells, and the efficiency and particularly cost is very important here. We try to replace the PT with other combinations of the materials. So in proton exchange membrane is very important like other membrane because it is working in the ambient conditions, but in the solid oxide or other, that is not the working in the ambient condition. It require high temperatures and also the other dependent parameters. So nowadays defined types of the card also available in case of the proton exchange membrane fuel cell, but the drawback is there, the cost and the efficiency and also the water management problem because water accumulation on the surface. So here we when we fabricate these materials, that ionic portion, conductivity, good mechanical stability, chemical stability, all those things we consider. Then finally we fabricate the anode and cathode. This is anode cathode. When we pivoted measures of the electrode proton exchange membrane, we used to use the membrane as a napkin for the proton exchange membrane fuel cell. This is the fuel cell structure stack where the membrane and gasket chambers, anode plate, cathode plate, all are there. And where if you see the hydrogens and oxygens, when it is coming, then it is produce the water, then produce the electricity here. So here, this napkin membrane, also polymer membrane, we are trying to synthesize in the labs scale, which restrict to move the other ion, only passing the hydrogen ion. So this is the treatment process of the carbon fabrication of the fuel cells, where the catalyst layer, membrane treatment, preparations of the membrane electrode, assemblies order there. Here we define types of the PTFE doping. We check for increasing the hydrophobic property. Then we check the contact angle of these materials. So where the contact angle will be higher, that means it's giving the higher hydrophobic properties. Then finally we check the current average contact angle, where which doping materials is giving the average contact angle high. Then the surface morphology we have checked. Then finally the higher materials of the percentage of the PTFE and perovskite materials we optimized. Then this is the surface morphology of the carbon cloth with coated with this platinum doped carbon materials. And then finally we check the current density and voltage of this solar fuel cells. And this is the fuel cells measurement circuit. And then finally we optimize the doping percentage of the PTFE, where we got the around 20% PTFE is giving the maximum percentage of the hydrophobic property of these materials. So here, if you see the cell potential current voltage, in case of the other materials, the Nafion doping is giving the maximum hydrophobic property. Also, it is giving the maximum current in case of the solar cells. So here we conclude that the catalyst layer with 20% PTFE loading carbon cloths showing this highest hydrophobic behavior, compared to the higher binding Nafion shows the higher contact angle as well as the highest hydrophobic behavior. Then the 180-degree thermal optimization we have done in the PBI polybenzene muscle membrane, that is giving the high cell performance. So this is the end of these fuel cells. Now we synthesis define these types of the nanostructures, perovskite materials, BAMA, BATiO3, also the methylamine lead iodide, and these types of the porous materials and composite materials we used to apply for these definitions of the device fabrications. So this is my part to conclude. Here my project is running, two projects still running. One is Mission Innovations and another is ACRBTR Teacher Association of Research Excellence. These two projects is still running. So here lastly I conclude one device fabrications, the water splitting the prototype device which I reported in the DST. This device, This is the auto lab that is cyclic voltammetry checking systems. Here the two storage is there, hydrogen storage and oxygen storage, and from presence of the photon, it's giving the output voltage here. Okay. So, and finally, I would like to thank DST, UGC, and DVT DST Joint Funding Scheme for giving me opportunity to work in this field, and my PhD student Abdul Moek and Orgute to help me. Okay, thank you.
Thank you very much, Dr. Subhashish Roy, for this wonderful presentation. He gives a brief idea about the functional nanomaterial for energy and environmental application. He started with the discussion of what is the nanomaterials, how we can modify this material to nanomaterials and their different properties. Then he discussed about 4 different topics. First, he go for the perovskite type of solar cell, mainly the hematite type of solar cell. Then discuss about the electrolytic water splitting system. Then discuss about the multiple state memory elements, and at the end he discuss about the polymeric electrolyte membrane fuel cells. I hope this audience enjoy this lectures very much. And if I go for the some quick question for this particular lecture by Dr. Subhashish Roy. So first question asked by someone who asks the what are the nanomaterials? This
What are the materials means?
What are nanomaterials?
Nanomaterials actually one dimension that should be below 100 nanometer. Okay, X, Y, Z. Any dimension that should be less than the 100 nanometers, that's called a nanomaterials. Here we used to define types of the perovskite materials for nanosynthesis purpose. That is, and we synthesize the top-down and bottom-down approach to get this nanoscale level nanomaterials. Particularly, its radius should be less than the board radius.
Then the next question asked by Shatindra Chada. He asks, can you explain what is the perovskite material?
Yeah, perovskite material, if you see nowadays, it is ABO3 structure. That means A cation, B is a center, and O will be the phase center, ABO3 structure. These types of the materials, if you see, this is the middle one, if you give some example like barium titanate, BaTiO3. BaTiO3, oxygen is present in the phase center, Ba presence in the corner, and Ti is the middle. So what is the main important here? The Ti in the middle sections, it can jump from upper to lower. So if it is jump, it can move from upper to lower. That means it gives the different types of informations of these materials. It can just store memories like 0101. Same like methylamine lead iodide. It is the organic, inorganic types of the perovskite. That means methylamine lead iodide. Lead is present in the middle and the iodine presence in the phase, and the methylamine CH3NH3 that is present in the corner. So if these types of materials is very important, this is methylamine that can move, that can change the positions of this structure. So if you see this material, we can easily tune this band gap of this material. That means whatever the zone of the band gap we can tune this band gap without compromising the absorption coefficients. That means we can, for these reasons, we can use these materials as the diode or as a photoanode, as a water splitting or a photo response materials. Okay.
Some question from my side. First question is, what is piezoelectric and why we choose the piezoelectric material for the memory elements device?
Yeah, a piezoelectric means when you give the pressure, it will produce the electricity. That means if you give force, if you coat one material of this piezoelectric and you put the pressure on the tops, it produces the electricity. That means pressure convert to the electricity. So in case of the memory device, multiphasic memory device, we have to change the property from the magnetic property to electrical property or electrical property to magnetic property. That means both are correlated. So how it will be correlated? Magnetic property, if you change, the electrical property should not be changed, because two phase is there, because electrical is one material and magnetic is different material. So in the piezoelectric, if you select the piezoelectric materials, it's if you put the pressure of the piezoelectric material, its orientation of the dipole will be changing. That means strain will be developed in the system. That strain will propagate the one property to other properties. Like piezoelectric magnetic properties will go to the electric influence with the influence to the electrical property. That's why the piezoelectric property importance here.
Next question is, what is the difference between the photoanode and solar cell?
Photoanode and solar cell. Okay, photoanode means you can use these photoanode materials. You don't need the photocathode here. In the water splitting systems, photoanode is another one things, and the counter electrode, that is the other things. But the solar cells, there will be the photoanode, there will be the photocathode, and in between, lots of the different types of materials should be there, so that it can produce the PIN junction. So in the photoanode cannot make the PIN junction to produce the solar cells. Photoanode only cannot produce. But in the photoanode, one part of this photoanode is the one of the part of the water splitting device. What the another counter electrode, if you use with this photoanode, it can produce the hydrogens in case of the water splitting. And on the top of the photoanode, if you go to its PIN layer and finally contact layer, it will produce this solar cells also. That photoanode means with absorb the photon, then this anode will produce the current in presence of the counter electrode.
And last question from my side. So you discuss about different type of structure, 132203. So what is that means?
Okay. 0303 structure means that is, if you have one matrix and three-dimensional structure, that will be the cover to the matrix 003 matrix. 2222 means layer structure, one by one layer, that is called the 2222 type structures. And 0322 and 01, if you see the 01 dimension, that means one dimension it is having the less nanometer, 100 nanometer, below 100 nanometer. That is called the one dimension nanostructures. Okay.
So thank you very much for your nice presentation and nice answer. Thank you very much, Dr. Subhash.
Thank you very much. Thank you.
So our next speaker is Professor Apurva Layak. Okay. Dr. Apurva Layak is working as a professor at Department of Mechanical Engineering, National Institute of Technology, Durgapur, India. Dr. Layak received his PhD from Indian Institute of Technology, Roorkee, India in 2008. Dr. Layak has experience of more than 25 years in this field of solar cells and others. Dr. Layak has published more than 115 scientific research papers in peer-reviewed journals and conferences. He has 10 book chapters of his credit. 7 research scholars completed their PhD under his supervision. He has handled many high-value sponsor and consultancy projects. He is a member of many professional society and a reviewer for many international journals. His field of interest is solar energy and alternative fuels. So I welcome Dr. Apurva Layak to present his. Sir. Please.
Good afternoon, everybody, all the participants and the dignitaries present over here. I'll take this opportunity to welcome you again in the recent advances in renewable energy and materials for sustainable energy future prospects. I'm going to discuss on solar thermal energy and its applications. The sun, that is the source of all the energies, whatever it is present over here, that may be thermal energy, that can be electrical energy, or whatever the forms of energies are present over here, it is the source of the mother source. It consists of hydrogen, helium, oxygen, neon, krypton, xenon, everything is present over there, and nuclear reactions, fission fusions are taking place over there. As a result, the core of the sun is having a temperature of few millions, and as a result, the surface temperature is in the range of 5,800 Kelvin. And because of this high temperature, it is emitting energy in the form of electromagnetic wave, and out of that total energy, only a fraction of energy is coming to our Earth. And that is the source of all the forms of energy in our Mother Nature, Mother Earth. And this solar energy, that can be classified into two categories: direct solar energy, or better to say, we're utilizing the solar energy in two forms: direct energy or indirect energy. The direct energy can be utilized in the form of thermal or in photovoltaic. Photovoltaic means the photovoltaic cells over which, when the solar energy strikes, it gets converted to electrical energy. And the other form, that is the thermal energy, that we are going to discuss here now. So that one can be captured by two methods, that is the flat plate collectors or by concentrating collectors. On the other end, the indirect form of energy, that what are the indirect form of energy? Just like the wind energy. Why that wind blows? Because when that solar energy falls on a ground or over the seas, etc., so that air gets heated and it moves up. And to fill up that space, that air from the surroundings, it tries to move to capture that space. As a result, it blows for that, and that is the source of that wind energy. Similarly, the tidal energy, how the tides are getting formed because of the attraction of the suns and the moons. We know it very well. So that tidal energy is also another form of indirect form of solar energy. Similarly, biomass, because of the photosynthesis, etc., some amount of energy is getting stored over there, and that ultimately gets converted into biomass. Similarly, OTEC, Ocean Thermal Energy Conversion Systems. What is this OTEC? Because of the sun radiation, the top surface of the ocean gets heated, and if you go to a depth of, let us consider 2 or 3 meters, so that water level is at a lower temperature. So this temperature difference can be used to convert it into our usable form, that is known as the OTEC. Now, what is that solar energy? Already I have told you, that is the sun is the source of energy, and it's a huge sphere, and that is providing that heat energy. And the energy, whatever it is reaching our Earth, is only a fraction, but still it is nearly 27,000 times than the present global demand. Means just by considering the solar energy, we can solve not only present but the futures, all the energy demand. Then what is the problem associated? The technology what we are having. So our duties, responsibilities start from that position. So this is what we see, that solar energy, it is not only the visible light, simultaneously the thermal radiation. If you go to that sunlight, we can feel it is hot. So it is a thermal radiation, not only the visible light, simultaneously UV rays, gamma rays, X-rays, so many things are, so all these rays are providing some amount of energy. And if you go beyond this Earth atmosphere, if you place over there a surface, let us consider about 1 meter square, that gets about 1367 watt per meter square. That is known as solar constraints. Now, because of the attenuations or the presence of these dust particles, moisture, etc., in this our atmosphere, the energy that is reaching our Earth's surface is less than that. It is in the range of 500 watt per meter square to 1000 watt per meter square, depending on the particular region. And based on that, we have to design our thermal applications. Now let us go through what are the advantages. Already I told you. So all the chemicals reactions and the nuclear fission fusions, everything is going over there in the sun. And only the solar radiation in the form of electromagnetic wave is reaching our Earth. Means it is a pollution-free, totally all these nuclear hazards, everything remains over there in the sun, and only the fresh energy is reaching our Earth. So it is a pure radiation form of energy. So we are very much lucky, better to say, to get this pure form of energy without pollutions, and easily we can convert to our usable forms. So whatever it is reaching our Earth, in another form, if you calculate it, whatever the energy that is falling on Earth in 30 days, that is having equivalence of the total planet's fossils, reserve, or whatever we have used, the total energy form. Means it's a huge source of energy. Only the thing, we have to make it feasible to convert it into our usable form. So the question is technology, whatever we are having. What are the disadvantages then? That sun does not shine consistently. Means during evening hours, during night hours, during rainy days, it is not available. So we have to think for some storage system in order to use that solar energy during those days. Or in other words, that solar energy is a diffuse source of energy. Means per unit area, how much of the solar energy is falling over there? It is very less. It is in the range of, even if it is maximum, means it is about 800 watt per meter square. It is not very huge. So we have to concentrate it so that we can use it. Let us take an example of a car. So how much of the energy is required to drive a car? So that much of surface area, whatever it is we are having, it is not sufficient to extract that solar energy directly and to convert into usable form. Means that car can be driven by that solar energy only. We have to take another source of energy in parallel. So that is diffuse source of energy. So that means related to the solar energy, if we are planning to utilize it, so some problems we are facing. Means our duty, responsibility being an engineer starts the collection of solar energy, how to convert into usable forms. Then the question of storage, because it is not having, we are not getting the solar energy consistently. So these are the problems we have to face. We have to sort out these problems. Now, in order to extract that solar energy in any particular location, so the automatically questions arises, can I use that solar energy in my location? The answer is yes or no, based on some factors, just like the latitude. What is latitude? We know it. But till, so what is the latitude of a location? Let us consider. So this is the location, right? So if we connect that location with the center of the Earth, the line that is making with the equatorial plane, the angle made by this line with the equatorial plane is the latitude. So if this latitude is more, that means we are moving towards the pole. So automatically the amount of the solar energy that is falling on that particular location is decreasing. So if it is very close to the equator, so the solar energy that is falling over there will be greater. Time of the day. During noon time, the sun remains overhead. So obviously, the amount of the solar radiation that is falling will be more. During morning or evening hours, it is slanting. So the amount of the solar radiation, amount of energy is less. So the position of the sun during summer, it remains overhead. During winter, it moves towards south because we are in the northern hemisphere. The reverse thing happens for the places southern hemisphere. So the positions of the sun that depends on the days of the year or for the seasons. So we have to take into consideration that one also when you are designing any solar thermal applications. Solar azimuth angle. What is that azimuth angle? Azimuth angle means, let us consider this is the surface over which that solar radiation will fall, or that is our applications. Right. So what is the angle that is made by this surface with the horizontal? So that is our tilt angle. That is here it is shown by the slope or the beta. Now let us consider, let us connect the sun with this center of the applications. That line, how much it is making angle. So let us consider this line. We are making a projections on the horizontal surface, and that line made by this projection, projections of that line with the due south. Let us consider this is the due south. This is the due south, and this is the line joining the sun with that location. And we are making the projection of this line on the horizontal surface. So the angle made by this projection with due south, that is our azimuth angle. Means it is facing south or not. It may be my applications are tilted towards east or west to some extent, so automatically we get less amount of energy compared to that of the if it is facing due south. Atmospheric transparency, it is also termed as attenuation because of the presence of the dust particles, moisture, carbon dioxide, etc. Some amount of energy is getting absorbed over there in the atmosphere. So if the atmosphere is much clear, so automatically my applications will get greater amount of solar radiation. And this is the global irradiation, means how much of the solar radiation that is falling in a particular location. From this figure, the red zones means more and more solar radiations are there. So I think it is very much clear that India is lucky enough. It is receiving more and more huge amount of solar radiations. So easily we can plan for solar thermal applications here. So what are the thermal applications possible? Just like the solar water heater. What is the solar water heater? When that water passes through the solar water heater, it gets heated. And this hot water can be utilized for bathing purposes or for kitchen purposes, etc., etc. There are so many applications are possible. Solar air heater, that hot air can be utilized for space heating purposes during winter. Otherwise, we are using electrical energy for room heating. So instead of that, we can go for solar air heater for the space heating, or we can use this hot air for drying purposes. Solar dryer or solar cooker. We are familiar with all these applications. Or it can be solar desalination. Desalination. Salinity of water can be converted to potable water for drinking water. We can convert ocean water, sea water, brackish water, dirty water into potable water by means of this solar desalination system. Or it can be solar furnace. So the solar energy that is falling over here on this furnace, and it is concentrating to an particular point or an area. So as a result, the temperature can be raised to any extent. And by this time, at this time, the temperature already we have achieved nearly 2000 degrees centigrade. Means by means of the solar furnace, even we can melt iron. And how much we can achieve? We can achieve this temperature up to the surface temperature of the sun. That is feasible theoretically, but till we have achieved nearly 2000 degrees centigrade, means that can melt even iron. We can use the solar thermal application, solar energy for the solar refrigeration and air conditioning. In solar refrigerators or air conditioners, it is not expected that always to consume electrical energy. We can use the solar thermal energy to run this. So how it is? We have to explain it in details. Thermal power generation. From thermal energy, from heat energy, we have to convert into power electricity. It is not photovoltaic. We are not discussing about the photovoltaic. Instead of that, the thermal energy to electrical energy, how it is possible. One option is solar pond, another option can be distributed receiver, or it can be power tower. The question arises, why we have to go for thermal options, right? So that for that, and study was there by the European Union, and they have they concluded, they've given us the result that nearly 2/3 of that energy requirement of the human beings for the industrial applications are of thermal in nature. Nearly 2/3 of the total energy demand is thermal in nature. Easily you can meet it by solar thermal applications. And out of that, nearly 50% is near at a temperature below 250 degrees centigrade. Easily we can meet it by solar thermal applications. Means most of the energy demand is coming under this category thermal, and at a temperature lower than 250 degrees centigrade, that we can meet it easily. What is the solar water heater system? Solar water heater systems, let us consider some solar water heaters placed at the top, rooftop, right? So the sun rays are falling over there, water is passing through that, water is getting heated, and it is getting stored over there. Now, when it is required, we can use it for bathing purposes, for kitchen purposes, etc. Or we can use it for space heating purposes also. So that is for the domestic purposes, for residential. So if it is a large scale, for the dormitories, for the swimming pool heating. So what is going on here? On the rooftop, we are having the solar water heaters. So that hot water is now passing through this, and it is going to the pond, right? And cold water from the pond, we are supplying it to the water heaters. So continuously it is running by the applications of the solar energy available over there, and this water of that pond is getting heated without any use of solar energy, electrical energy. So what are the things there in the solar water heaters? It is basically two things: solar collector and a storage tank, and nothing else. And what is this collector? Collector, let us go to this figure. Collector is like this. A sheet is there. Let us consider this sheet, metal sheet, GI sheet or copper sheet. It is, the top surface is painted black. The below this surface, below this sheet, on the down other side of this sheet, some tubes are there. Okay, so many tubes are there. They are welded just below the surface, right? Now, when the solar radiation is falling on this black surface, it is painted black, so automatically whatever the solar radiation is falling over there, it is getting converted, it is absorbed, getting converted into heat. Now, this surface is getting heated. Now, when the water is flowing through these tubes remains welded just below these sheets. So automatically the tubes are also getting heated. Now, when the water is passing through these tubes, they are getting heated, and the hot water will come out on the other end. And from the bottom side, another larger diameter tubes are there, which the cold water is entering through these tubes, it is rising, and it is moving from the other end. So we are getting that hot water from the top, right? So that design, it is like this. So just below the surface, we have welded so many tubes, right? So that through these tubes, the water is passing and it is getting heated. And in order to minimize the heat loss on the bottom side, we are providing here some insulation, right? It is so simple design, nothing else. That solar water heater is placed over here, and that hot water is moving up, and it is getting stored over there in the tank. Now, when that hot water is required for our domestic purposes through this end, by opening our tap, we can use it. And in order to make up that much of volume, we have to supply the cold water to that one. And continuously, this circuit is running, and that water is getting heated, and it is getting stored over there. So that can be utilized for domestic purposes, to run our kitchens, to run our bathrooms, etc. Now, let us consider, someone may ask, because during evening, sun is not available, or during rainy days, it is not available, then what we will do? We have to depend on some other systems. No, it is not. So what we have to do? We can make an auxiliary along with that solar system. What is the solar system? The solar water heaters that is supplying that hot water to the tank, and that circulation is taking place. Along with that, additional and auxiliary heaters. That auxiliary heaters is run by a conventional fuels that can be electrical energy, that can be by burning coal or wood, etc., etc. So this hot water, so this heat will be supplied to the storage tank, and when it is required, we can take it. Means just from the same system, we are supplying that hot water to our bathrooms, to our kitchens. So it is for the domestic purposes. Now let us consider, so these types of domestic systems are mounted on the top of our roof, and all are producing this hot water, and that is getting stored in a central storage tank. So whenever it is required, each and every members of the community, they can utilize it easily, right? So it becomes an district solar air heating system or a city solar air heating system. So what are the other types of flatbed collectors possible, right? It is unglazed. What is the unglazed? Now the question of glazing is coming into picture. Here the system was having a glazing, a cover by means of a glass. So why that glass is there? Because that heat that may try to release heat, some heat losses may take place from the side. So we have provided a glass over there, right, to minimize that heat losses. Now the sunlight that is passing through this glass, falling over there on the blackened surface, getting converted to heat, getting absorbed by this water. Now, because of the temperature of this surface, it will also try to emit energy in the form of electromagnetic wave. But what is the temperature here? The temperature will be in the range of 70, 80, 90 degrees centigrade, hardly not more than that. So automatically it can emit some amount of energy, but this glass is there. So what form of energy is coming out? In the form of electromagnetic waves. And that electromagnetic wave is coming from a source of 70 or 80 degrees centigrade. It is of large wavelength that can't pass through this glass. But when the sun radiation is coming, that the source is 5,800 degree Kelvin, high temperature source. So the wavelength of the sun radiation is small. Easily that sun radiation can pass through this glass, but the radiation coming out, the heat losses, otherwise that may try to come out through this glass, it can't pass because it is of long wavelength. So that's why we are providing a glass that is termed as the glazing, right? So this glazing, if the glazing is not there, so automatically losses will be more. But the glazing is the main component or the most costliest component of that solar air heater. So they have avoided it in order. Yes, they are sacrificing some amount of the performances, but the cost decreases. Right? So in this case, some standard flatbed character, the plate is there, glazing is there, and the below that insulation. Instead of one glazing, we can go for two glazing also. Right. So in that, so many variations are possible. Here, some spaces have been provided, and through this duct, air is passing. So that becomes air heater. Okay. So these are the glazed collectors. Means glass is there. They are unglazed, open. The losses will be more, but the cost is less. So installation have to whatever may be the location. Suppose it is in the northern hemisphere, so we have to place our applications towards south, facing south. If it is in the southern hemisphere, that will have to place facing north. Why it is? In order to capture more and more solar energy, right? And simultaneously, some tilt angle is required. Tilt angle, what is the tilt angle? Already I told you, right? Here it is. Tilt angle was that beta, right? Yes, that beta. So that beta, what should be the beta? It's a thumb rule. So that if the tilt angle is equal to that of the latitude, then the solar radiation that is falling over a particular surface will be maximum. So this is the evacuated flatbed collectors. So what is this evacuated tube? It is a very latest design at this moment. Evacuated tube means just let us assume two tubes made of glass diameters. Let us assume two tubes having different diameters made of glass. Now let us take the smaller tubes and paint the outer surface by some black paint. We are considering the smaller tube and we are painting the outer surface by black paint. Clear? Now let us enclose the smaller tube inside that big tube. Clear? So it becomes two concentric tubes. Now let us seal this end and the other end. So what remains in between? Some space, and this surface already painted black. Now let us evacuate this in this space, right? In between these two tubes, that space we are evacuating. We are trying to remove that whatever the airs or anything remains left, we are trying to evacuate it. Now, what is the advantage over here? Now, when the sun rays are falling over there on the black surface, it is getting absorbed, it is getting converted to heat. Now, when the air or water, it is passing through these tubes, so that will get heated. Now, as in between these two tubes, it is evaporated. So, what will happen? No convection loss will take place, because from this surface, the heat have to move to the outer surface, outer tube. Only then that losses may take place from the outer tube to the atmosphere. It is not feasible. Why not feasible? Because in between these two tubes, nothing is there. It is evacuated. So the convection is arrested. So that will decrease the heat losses. So by means of this evacuated tube, the performance of the system, efficiency of the systems will be good enough, more than the conventional design. And let us go to the solar air heater. Air to be heated, and that hot air can be used for space heating, for crop drying, or industrial applications. Right? Now let us consider this type of one duct we have generated, and here I have placed an absorber plate. This absorber plate, this is the plate placed over there. That is, let us consider GI sheet or copper sheet, and the top surface is painted black. Right? So this absorber plate is a metal sheet, GI sheet or copper sheet, and the top surface is painted black. Right? And the whole thing is covered by means of a glass glazing. Now air can pass through this duct. So through this space, the air can pass. Now when the air is moving through this duct, as this top surface remains exposed to solar radiation, so the solar radiation is falling over there on this black surface, it is absorbing the heat, and it is getting converted to solar radiation is getting absorbed and getting converted to heat. Now when that air is passing through this duct, it is getting that heated. Now on the other side, hot air will come out. So that is known as solar air heater. So this space heating purposes using liquid fluctuating collector, water heater, by using water heater. Let us consider this is the water heater placed on the rooftop. Sun radiation is falling, water is getting heated, hot water is coming out and getting stored on this storage tank. Now that hot water can be circulated through the circuit, and when cold air is passing over that to this circuit, so automatically it is getting heated, so that space will get heated. So by means of this technique, by means of this method, easily you can heat up that space. So what are the other methods possible to heat up that space? So this is our solar space heating by rock bed storage system. So what is that? So let us consider this is our room. I have to heat up that space. For that, solar air heater is placed over here. Means this is the glass, and just below this, the absorber plate that is painted black, and through this passage, air can circulate. When the solar radiation is falling on this black surface, it is getting heated, and this hot air is moving up, and it is entering to the space. On the other side, cold air from that room is entering passing through this passage, and again it is moving through this solar air heater to get heated. So this circulation is continuing, and our space is getting hot air continuously. Suppose it is not required, I want to stop it. So that's why a damper or the bulb is there, so I have to close it. Purpose is served. Now how the system will run during evening? So that's why it is rock bed is there. Now these rock beds, we know that rocks also store some amount of energy. During daytime, they are getting heated automatically. Now when this circulation should take place during evening, the rock beds will release that heat, and this air is getting heated, and this circulation should take place during evening. But the night time also will feel comfortable to have this continuously the circulation of the hot air. The application of solar radiation for the solar dryers. Solar dryers are used for drying purposes, drying food crops. Let us consider what are the food crops. Generally, we are drying it in open sun drying, generally on the open ground or in the rooftop, generally in the villages, they are doing it. Let us take the example of chilies, red color, good chilies are there. We have produced it in our farm. And when we are drying it in the open ground, and it takes long time, nearly 10 to 15 days to get dried totally. But what happens? Some dust, some insects come in contact, come in contact, so automatic. And in addition to that, the color of this red color, good bright red color, vanishes, becomes to some extent some grayish in color after 15 days. So automatically, if the farmers are going to sell it to the market, they are not getting good return because of the color. It can't be that MDH, that type of quality. It is not possible. Then what to do? So if they are now, so the option is solar dryer. So what is solar dryer? So this type of one cabinet let us produce. It is having some trays over there, and these trays are perforated. We have placed these chilies or grapes or cabbages, etc. over there, and we have closed it. Now the solar radiation is passing through this glass, and inside this cabinet it is painted black. So automatically it will absorb the solar radiation, it converted to heat, and some perforations are there on the bottom also. So through these ends, air can pass through, and it is taking out the moisture and is leaving the system from the top side. So this circulation is taking place continuously as it is enclosed. So automatically, the temperature inside this cabinet will be much more than the open drying. As a result, it will get dried up quickly. It will not take 15 days, but by 2 or 3 days, it will get dried totally. As it remains in the sun for 2 or 3 days, so automatically color remains preserved. Now they can get good return from that one. Now that was for the domestic purposes for a particular family, small size. Now I want to make it industrialized. I want to make it larger size than what I have to do. So let us design a cabinet like this, any size as per your wish. Now let us put here some solar air heater, right? In this figure, only one I have shown. Let us consider a number of solar air heater placed side by side. All are getting or generating hot air. So this hot air, now we are supplying it to this cabinet, where in these trays some chilies or cabbage or grapes have been placed. Now this hot air is passing through this, taking away the moistures, so easily it will get dried. Now the beauty here, so the solar radiation is not entering to this cabinet, only the hot air. So they are not exposed to sunlight. So the question of losing this color will not be there. So by this method, not only the foodstuffs, we can dry timbers, tea leaves, anything. So the question of the tea leaves, when arises, the quality depends on the smell and the taste. So as it is not coming in contact directly to the sunlight, so they get preserved. So automatically the question of quality will be very high. And by means of this method, already we have achieved a system that can dry even raw bricks, brick clean. In brick clean, we are also using this type of system, solar dryer. That is possible. Now let us go for another application, that is the solar distillation, desalination, or still, S-T-I-L-L, still, the same thing, solar distillation system. What is the solar distillation system? By means of the solar distillation system, we can convert seawater, ocean water, brackish water, saline water into potable water. What is the application? Let us take the example of Gujarat, Kutch area. They are facing severe potable water, drinking water crisis. Or let us take the example of Arabian countries, they don't have potable water, drinking water, but it is surrounded by oceans. Then why that shortage is there? Because they are having ocean water, saline water, salty water, but not the drinking water. So what this solar distillation system can convert the seawater, saline water, salty water into potable water, drinking water. How it is? Let us go through this. So let us consider for domestic purposes, 1 meter by 1 meter, one basin is there. And the inner side of this basin is made of some metal. Let us consider it is GI sheet or copper sheet, and that inner surface is painted black. Where we are keeping some brackish water, saline water, salty water, dirty water, and it is covered by means of a glass. That can be a single cover, or this way two glass can be there, no problem. Now, when the sunlight is entering to this space and falling over there on this water, as it is painted black, so automatically that will absorb the solar radiation, it will get converted into heat, and this water will get heated. As it is getting heated, so automatically evaporation will take place, evaporation. The same way, natural hydrological systems also runs, the way the rains takes place, right? So this, from this space, from this water, that evaporation takes place, evaporated vapor will move up, and then get condensed on the lower side of this glass, and it will form some droplets, and that droplets will move along this glass, and that will get collected on this condensate channel, right? And this water, we have to collect it. That is distilled water, pure distilled water. Nothing is there, only water. Easily I can use it as a potable water, drinking water, because we are having the scarcity. So easily we can convert it. Now, how much of the water will get it from 1 meter by 1 meter basin? That is in the range of 3 liters per day. So if we are having 4 members, so we have to think for 2 meter by 2 meter, that will serve my purpose, right? So if for a community purposes, based on that exercise, I have to multiply it in order to have this potable water. So that is the solar steel, the prototype. So the same things, only the heat transfer, how the heat transfer is taking place, that has been shown over here. So because of the solar radiation, some amount of the energy is getting used to evaporate the solar radiation, water, and that moves up and comes in contact with this underside of the glass and gets condensed, forms water droplets, and that moves along this glass and get collected on the distillate channel. This is the solar cooker. Now, nowadays, our villagers, they are using it. Let us consider what is this size, how it looks like. Let us consider it is about 1.5 feet by 1.5 feet, and depth is about 10 inch, right? So that type of and box that can be made of wooden, no problem. Or at that inner surface, that inner side is made of GI sheet, okay, or copper sheets, and this inner side is painted black, and that has been covered by means of a glass. Okay, this is by means of a glass, and inside this box I have placed some metal box that can be our tiffin box, and the outer surface of this tiffin box is also again painted black. Now, when the solar radiation is falling, passing through this glass and falling over there inside this box and on this tiffin box, right? So that will absorb the solar radiation, get converted to heat, and inside this tiffin box or metal box, I placed some in a box. Let us consider I placed some water and rice. In another box, I placed some vegetables and water. Right. So in that way, in 3 or 4 boxes of this, I place different types of foods. And if I keep these things in the open sunlight for sometimes about 2 hours, what will happen? The solar radiation is getting concentrated over there. The temperature is rising, and the temperature in this situation will be in the range of 125 degrees centigrade. And that is enough to boil your food, to prepare your rice, to prepare your pulses, to prepare your vegetables, right? Without any fuel. So that is solar cooker. And the cost of this system is in the range of, at this time, depends on the quality of the material or the type of material used, depends on in the range of 1,000 to 1,500 rupees only. and they are utilizing it. So it's a pictorial view. So 3 boxes have been placed over there where we can keep our foodstuffs, and that will get prepared, right, easily. Now, what are the disadvantages of the system? As already I told you, that the temperature is in the range of 100 to 125 degrees centigrade. So we can prepare, we can boil our rice, we can boil our pulses or the vegetables, but we can't prepare our chapatis or puris. It is not possible. Fries are not possible. Because in order to do all these operations, all these types of cookings means chapatis, puris, fries, etc., higher temperature is required. So by means of these types of box type solar cooker, it is not feasible. So that is the drawback. But I am an engineer. I have to sort it. I can't wait or leave it unattained. So what I have to do? Then I have to go for concentrating type of collectors. Now let us consider what is the theory behind. So it's a concentrating type, just like this antenna. So where the solar radiation is falling, and that is concentrating on a particular point where I have placed my cooking pot. So automatically the temperature can be any extent depending on the size of my these concentrating collectors. So by this method, the temperature will be much higher, whatever it is required for the frying or the chapatis, etc., etc. But the question arises, then I have to be in that sun continuously in order to prepare my food. It is not desirable. So what I have to do? In that way, that's why I have to do this type of design. So let us consider I am placing this collectors over here so that it is concentrating it through a window to my home, to my kitchen, and where I have placed my cooking top, right? So the temperature will be to any extent depending on the size. So as a result, I can prepare my food, that foodstuffs, etc., whatever it may be. Even I can prepare my chapatis, puris, etc., the fries. And depending on the size of this collector, the amount of the heat depends. So it can be increased to any numbers. It is not only for a family, but for a community people is also possible, for the hostels, hospitals, etc., etc. So this is another design. Instead of a flat plate collectors, let us consider the parabolic type of collectors are used over there. So it is generating that hot water or hot oil or whatever it may be. If it is flat plate collectors, so the hot water will be available. If it is a concentrating collectors, let us consider hot oil is available. So that hot oil is being supplied. And now I am opening this valve A and B. That C is closed. So through this A and B, that hot oil is coming over here. So that this where I have placed that cooking pot. So the cooking pot is getting heated. Now I can prepare my food. Now after releasing that heat, that will come back and entering to the solar collectors again. So that circulation is taking place during daytime. During evening times, what will happen? Sun is not available, but the storage tank. Okay, so when you are preparing our lunch, let us consider during 10 to 12, right? During 10 to 12, this circulation is going on. Then what about 12 to evening 4 or 5? What we will do? So that solar radiation at the time, it is getting heated, so that hot water or hot oil is being supplied to this pebble storage, right? So this much of circulation is going on. When that solar radiation, we are not utilizing it for our cooking purposes. So the storage is storing that amount of energy. In the evening hours, when the sun is not available, at that time, what we'll do, we'll open this valve A, B, and C, 3 opens. Now from this storage tank, it is coming through these valves to the cooking pots, and this much of circulation is taking place. That is possible. That means that can meet our demand throughout the day. So this is these are some applications of the solar cookers. Shantiban at the top of the Mount Abu, where 84 types of receivers are there, and that is having about 650 degrees centigrade. That can prepare about 40,000 meals per day. Not only a small hostels of the hotels or the hospitals, 40,000 of people are getting their meals every day. Tirumala Tirupati, they are preparing 70,000 meals per day. They are having numbers of dishes placed on the rooftop. And this is the Sai Baba Sansthan in the Maharashtra city. So that is preparing on the regular days 30 to 35,000. In some occasions that goes beyond 1 lakh meals per day, and they are having, so these types of some dishes placed at the top, and that is also running at a temperature of 650 degrees centigrade temperature. Means even if we place something over there, that starts burning. So we are having let us go through a video. I think that will be better clear, and that may okay. So it is the Asia's largest solar heating cooking systems. Now let us come back to our presentations once again. So solar absorption refrigeration system. Solar refrigeration, how that refrigeration system without any electrical energy, how it can run. Let us consider numbers of flat plate collectors are placed there side by side. Numbers of flat plate collectors. They are producing hot water. That hot water can be fed to this one. So this is the source of heat only. And this is the absorber. This is the absorber. Let us consider the absorber. Means it is filled with ammonia and water solution. So this is filled with ammonia and water solution. When it is getting heated, so the ammonia will come out. So the ammonia gas is coming out. If the temperature is more, the pressure will be more. So that high pressure ammonia gas is coming out from this absorber, from the generator. From the generator, it is coming out and it is moving. Now it is a condenser. Cooling water is provided. So this hot ammonia vapor is getting condensed, getting converted to liquid, but the pressure is high. So the high pressure liquid ammonia, when it is passing through this throttle valve, that it is the expansion valve, throttle valve, so what will happen? Sudden expansion. And due to this expansion, what will happen? Liquid ammonia will try to absorb the latent heat of evaporation. It will try to absorb the latent heat of evaporation, and that is passing through this space to be cooled. Wherefore, where we have to maintain lower temperature. So this ammonia vapor is trying to absorb the latent heat of evaporation. Wherefore, from this space, when it is passing through the circuit, so automatically it is absorbing the heat from that space. Its temperature decreases. That is our motto. Now, what happens to this ammonia vapor? It gets heated. It gets vaporized. That vapor is now entering here, where we are supplying cold water. Where from water we are getting it? From this, it is passing through the heat exchanger, right? Getting converted to cold. Now that cold water and this ammonia is coming in contact. Water is having, this ammonia is having good affinity towards water. So that gets absorbed over there, mixed over there. So what happens ultimately? It is getting collected in the form of water ammonia mixture. That ammonia mixture, ammonia water mixture, now again we are pumping it with this end to the generator, where due to this heat, it is getting evolved. It is coming out in the form of the high pressure gas, ammonia, that circulation. So here, The question of electrical energy is not there and the system runs. So we are maintaining a cold space. Cold space means that can be our room. If it is a room, then it is the air conditioner. If it is a refrigerated space, it is the refrigerator. So it is the solar absorption refrigeration system. So easily we can run it based on the solar radiation, solar applications. So what are the power generation? So we have seen solar distillation, solar cooker, solar water heater, solar air heater, so many things. But how to convert it into electricity? Yes, it is possible. And that can be classified into three categories: less than 100 degrees centigrade temperature, that is the low temperature systems. If it is 100 to 400, then it is a medium temperature system. And if it is high temperature system, means more than 400 degrees centigrade. And in case of low temperature applications, that types of flat plate collectors, temperature less than 100 means water. Okay, so flat plate collectors can be used, or the solar pond or the solar chimneys can be used. And in medium temperature means 100 to 400 means parabolic collectors to be used, because I have to raise the temperature more than 100, means that the water can't serve that purpose. Okay, so it is parabolic type collectors. And if it is more than that, so the parabolic will also not possible. So paraboloidal disc like structures have to be used. So paraboloidal disc or central receiver system. So how it works, let us go through this. So low temperature applications, so numbers of flat plate collectors are there. They are generating hot water at a temperature, let us consider 90 degrees centigrade. Okay, so that is passing through the storage tank, and this circulation is going on. And in this tank, let us consider something is there, that is freon. Okay, so the freon is having boiling temperature. At what temperature? Very low, in the range of 10 or 20 degrees centigrade, like that, or some organic liquid I can use over there. So that gets converted into vapor. So that hot, high temperature, high pressure vapor of that thing, right? That can be your organic fluid, or it can be anything else, right? So that is passing through this, and that is passing through this turbine to convert it into mechanical power, and a generator can be coupled over there to convert into electricity. And after doing its works, that is passing through this condenser, again it is, so this circulation is taking place. But the problem associated with this is at what temperature it is running? Hardly 90 degrees centigrade. And what is this atmospheric temperature? 25 degrees centigrade. So the temperature difference is very less. So the hot water Rankine cycle efficiency in the range of 2%, along with this percentage of this one. So ultimately, the overall efficiency of the system will be in the range of 1% only. So it is not efficient system, and as a result, no commercialization takes place still, because of the system efficiency is very less. Let us think about the solar pond. This is the solar pond where we are maintaining different salt concentrations. How it is possible? How it is possible? At the top surface, it is maintaining low salt concentration. At the bottom one is the high salt concentration. Means we are providing continuously salt over here, and due to this, it is having a tendency, so it will try to get it mixed. So from the top surface, we are removing some amount of the salty water and continuously supplying that fresh water over there. So this temperature, this gradation, so density difference always gets maintained. As if now when the sun radiation is falling, and this pond is covered by means of some plastic, black plastic, low density plastics, high density plastic, whatever it may be, it is black. So when the solar radiation is falling over there, it is getting absorbed, it is getting converted into heat. Now this water will also get heated, but that is high concentration, high salt concentration. Means it will, when it is getting heated, it will try to move up, but as the concentration is more, so it can't move up. So it gets arrested over there. So the high temperature water remains stored over there, and the top surface is at a cold temperature. Now this hot water can be circulated through this end in order to provide it to this organic working fluid. Means organic water working fluid that is having a boiling point, let us consider 20 degrees or 30 degrees centigrade. So automatically at this temperature, it will get superheated, so that vapor of organic working fluid is coming out. When it is moving through these turbines, it rotates, converted into electricity. After doing its duty, it is moving through this condenser, again coming back to this boiler. Here it is the evaporator for this one, and it is the boiler for this one, right? So that is the low temperature applications by means of, again, a cooling point. But what is the temperature difference? What is the temperature generated over here? Hardly 90 degrees centigrade, and it is the atmospheric temperature is 25 degrees. Again, the same thing. So the temperature difference is less. Rankine cycle efficiency will be less. Overall efficiency, that's why it is very poor. So no commercialization takes place. Only we are making some prototypes, some pilot plant in some universities or for research purposes, till no commercialization takes place in the whole world. So this is a pictorial view of University of Texas based on solar ponds. And this is a solar chimney. What happens? Let us consider a chimney. A tall chimney is possible, having a diameter of 10 meters. Let us consider 10-meter diameter, and that is and it is placed on a field, and that field is covered by means of a plastic sheet or glass sheet. Okay, and this field can be of a size of, let us consider, 200-meter diameter or slightly higher, no problem. Now the solar radiation is passing through this glass or the plastics and falling over here. So automatically this zone will get heated, right? And that hot air will try to move in this direction. And to take that space, so cold air from the outside, it will enter. So continuously this flow will take place. And if we place a turbine over there, so turbine will rotate and get converted to mechanical power. So if you couple the electrical generator, so that will convert that energy into electricity. That is possible. But the question is how much? So that has been explained over here. So if we can generate a chimney of 200-meter height, so already it is done. So how much of the power will be produced? We can compare it with this one. So this is the Burj Khalifa, 818 meter. So if we can generate a 500-meter solar chimney, that will produce about, this is 50 megawatt, so hardly 20 megawatt. Now constructing a chimney of 1 kilometer height, is it feasible? So if it is feasible, I can give you this much of power, right? 750 meter solar chimney can produce a power of 50 megawatt. If it is 1 kilometer, about 200 megawatt, that is possible. But the question of the constructing this height of a chimney, constructing a Burj Khalifa, how much costly, I think we know it very well. So that's why this is a project still we have not commissioned. We are not thinking even. It is so costly, it will be so costly, so it will not be economically viable at this moment. So what is the medium temperature applications then? So if that solar, that low temperature applications are not technically viable, economically viable, then what to do? Can we go for medium temperature applications? Okay, let us think for. So what is going on there? Parabolic types of collectors are there that is concentrating the solar radiation in a particular line through which some oil is passing. So automatically the oil will get heated. So in this way, so through this tubes, it is where that solar radiation is getting concentrated. So by this way, we can generate the temperature of about 400 degrees centigrade. Now this 400 degrees centigrade oil, when it is passing through this system, that is nothing but our boiler. So we can get steam at a temperature of 400 degrees centigrade. That 400 degrees centigrade steam, if we fed it to a steam turbines, so automatically that can generate some amount of power, electricity is possible. But the question is, till it is not commissioned or economically viable. Why not? Because again here the temperature difference is nearly 400 degrees centigrade maximum possible, not more than that, right? And the commissioning cost, because so many collectors are required, so initial cost will be very, very high, and the rest portion is nothing but our steam-based power plants, nothing else. But the commissioning cost will be very high, so that's why we better to say we can't afford it at this moment, and it is automatically to generate 1 unit of electricity will be much more costlier than the present system. Then let us go for the high temperature applications. Is it feasible over there? So what is that high temperature applications? Let us think about a speed of 1 mile by 1 mile, where these types of numbers of mirrors have been placed. These mirrors are termed as heliostats. So where the solar radiation is falling, and that is concentrating that solar radiation on a particular space, where I have placed a boiler or a receiver or a tank, where where water is placed over there. Now this water will get converted into steam. That steam is passing through these turbines to produce electricity. Easily it is feasible. So how much is the temperature can be attained? That depends on the numbers of heliostats or the mirrors placed over there, right? So if the numbers is more, so the temperature will be more. I can attain by this way to any extent, any temperature. It is possible. So that is feasible technically, but the problem is the height of the system is more, so the construction cost is more. At this time, we don't have, we are having some applications, particularly in US, Sandia, CRTF, or California Bastro. We are having some units. They are having capacity of 10 megawatts or 50 megawatts like that, but big size installation still we are waiting for, and we have to make it feasible. So solar power towers. So in the tank, instead of water, you can use some salts also. That salt get molted, so that will take away the heat. So in that way, there are so many research are going on in order to absorb that heat. So what are the advantages of the solar thermal applications? So the solar thermal systems works efficiently at low temperatures as clean energy, and the flat cutters can work economically. Reflective surfaces needs broad acceptance on gas, so that's don't cost too much, and the reflectors must be kept at clean frequently. You have to make it clean. Washing is required. So reflectors should not or be wise in headstrong countries. Means if the problems are there, so we have to be careful. Now at this moment, so what are the take-home points? Let us go through. So solar thermal systems are cost-effective at low temperatures for water heating or cooking, and we have make it feasible, technically feasible, economically viable. People start using it. Solar dryers, solar cookers, solar ovens are relatively inexpensive, cheaper. Cookers are cost in the range of 1,000 rupees only, or even lower. Water heaters, we have already commissioned it in most of the hostels, hospitals, everywhere. So the power towers electricity cost at this moment is too high to compete with the photovoltaic systems or the coal-based power plants. So that's why we have to devote more to improve it. So the research, it demands research in that particular field. Massive power towers can yield up 10 megawatt, while typically utility plants that can be generated in the range of, that can be designed in the 500 to 1500 megawatt at this time, which is possible. So that Bastro, that is in the range of 10 megawatt only. So we can't think for much higher because it will require high tall towers for that. So these are the problems associated with that. And now our duty, our role starts from that positions in order to improve it. Now let us go through a quiz. Identify the correct statement. PV cells use the heat from the solar energy into heat. Or the solar thermal means conversion of the solar energy into heat. Wind is a direct form of solar energy. Solar thermal energy use causes a lot of pollution. Which one is correct? I think PV cells use heat from solar energy into heat. No, it is photovoltaic. It converts the solar energy into electrical energy. So it is wrong. Solar thermal means conversion of the solar energy into heat. So that is correct. Wind is an indirect form of solar energy, right? Because of that heat energy, because of solar radiation, air moves up, and to take up that space, that surrounding air move towards that space. So because of that, the wind takes place. Right. So it is indirect from solar energy. Solar thermal energy causes a lot of pollution? No, not at all. It do not cause any pollution. A solar collector should face in India towards south, because we are in the northern hemisphere. Solar thermal energy cannot be easily used for these purposes. Cooling, yes, solar cooling. We have seen solar refrigeration, solar air conditioning, water heating. That is also possible. Solar drying is also possible, but running a car is not feasible. Why not? Because the surface area of the car, whatever it is, if we multiply it with 1000 watt per meter square, so that much of maximum energy is available. Out of that, we have to convert it into usable form. So it is not enough to drive a car. The most important component of the solar energy system is the glass wool insulation. No, that is to minimize the heat losses. Pump? No, not at all. Collector, that can be. Piping is not the most important component. So the collector is the most important. Collector and the storage, they are the most important. Tracking of the collector is similar to, tracking means we have to fetch this applications towards south, towards the sun. So that is very much similar to our sunflower turning in the direction of the sun continuously, right? So that is termed as tracking. In case of parabolic collectors, paraboloidal collectors, continuously you have to track it towards the sun in order to capture more and more sunlight. A box-type solar cooker cannot be used to make rice, cake, potato chips, dal. Dal is possible, rice is possible, cake is also possible because that does not require high temperature, but the potato chips is not possible because it is frying. Higher temperature is required. Solar steel is a device to make hot water, no. Dried food, no. Pure water from seawater. Distilled water, yes. Okay, that's all. So whatever we are thinking, no problem, but the ultimate solution is the sun, because that is the source of all the energy, whatever we are having, and in future, whatever we are planning to have. Okay, that's all. Now, if you have any queries, okay, let us try to discuss it. Oh, what is azimuth angle? Azimuth angle, Mr. Sumit Kumar Bhattacharya. What is azimuth angle? Azimuth angle means, let us consider I am having a flat plate collectors, right? So the normal of that flat plate collectors, what is the normal? Normal of the flat plate collectors, can I draw it? Now I have to make the projection of the normal on the horizontal surface. Can we do that? So I am making the projection of the normal to the surface on the horizontal surface. Clear? So that projection, how much angle it is making with the due south? Is it facing south or towards, to some extent, east or west? So how much angle it is making? That angle is known as azimuth angle. Means if it is 0, it is facing south, means it will get more and more energy. Just like that. Okay. Which angle you are specifying as beta? Beta is the angle between that surface with the horizontal surface. That is nothing but the tilt angle. At what tilt you are placing it to capture more and more sunlight, right? Suppose it's an horizontal surface. Then what will be the beta angle or the tilt angle? It is nothing but 0. We are making it to some extent angle. So that's why what is the angle between the surface and the horizontal surface? That is beta. Sir, Anirudra Prasad Jadhav, you have asked why you put wind, geothermal, biomass, etc. under indirect form of energy. Yes, they are renewable form of energy, but ultimately they are indirect form of solar energy, because ultimately they are getting that energy from the sun. Just like the biomass, because of the photovoltaic, photosynthesis, etc., that energy remains stored over there. That is ultimately we are getting in the form of biomass and nothing else. Similarly, geothermal, geothermal is also one form of what is the geothermal? Let us consider that molten metal, whatever it remains, molten material that remains inside the earth core. Okay, that is the source of geothermal. Where from it comes? It is coming from that ultimately from the sun, right? So mother is nothing but the sun. So it is also one form of indirect form of geothermal energy. Wind, already I told you. Because of that sun energy, because of the sun radiation that is falling on a particular area, that wind and that air try to move up because it is getting lighter, right? And to occupy that space, the surrounding air is moving towards, rushing towards that space. And as a result, the wind blows. The generation of the wind energy coming into picture. So the wind is indirect form of solar energy. If the sun is not there, so wind will not blow. Got it? And the next, Amit Chandra, can you say something on photovoltaic cells, its technology and technicalities? Yes, that is possible, but today's topic is on solar thermal applications, because the photovoltaic, some problems are there, some advantages are there. So photovoltaic cells means when the solar radiation is falling over there, it is directly converting into EMF, that electricity, and numbers of cells we have placed side by side, and ultimately the as a total, whatever it is, all are producing, that we are using as an energy sources, right? And it is also having some problems because the silicon extractions from whatever may be the sources, it is very costly. As a result, photovoltaic cells are also very costly at this moment. Research is going on in order to minimize this cost, means in order to have a technique or some systems so that we can extract that silicon easily, cheaply. So many research are going on. Even at this time, we are trying to have the silicon from rice husk. Okay, so that is a research are going on. So in nearest future, so we can expect that the cost of the silicon extractions will decrease. So automatically the photovoltaic cells cost will decrease. Then that energy, whatever we are getting it from the photovoltaic cells, will be cheaper. Okay. Is it clear to all of you? Anyone else? Okay. Mr. Shatinder Chadha. Is absorption refrigeration used commercially? Yes, it is. It is possible. We are doing it. We are using it in remote places. Not only in remote places, in earlier days when that electricity was not easily available everywhere, at the time we were using these absorption types of refrigeration in most of the hospitals to preserve their medicines. In remote places, even till today, we are using it, this type of solar absorption refrigeration system for refrigerator. Okay, thank you.
So thank you very much for Professor Nayak for his very informative and nice presentations. So he mainly talked about the solar thermal system. He started with the what is the solar energy system and its importance in direct and indirect energy forms. Then discuss about the advantage and disadvantage of the solar energy system. And then he moved on different type of solar energy thermal system. Like it started with first the water heater, then goes for the solar air heater, solar dryer, solar distillation, solar cooker, solar absorption, refrigeration system, solar pond, solar chimney, and last discuss about the solar tower with their basic working principle, what is the advantage and disadvantage, how it is equally possible or not. So we very much thankful to Professor Nayak having with us with this very much information talk. Thank you, Professor Nayak.
Thank you, Dr. Anand.
So now I hand over the mic to Mr. Manush Mujumdar for his vote of thanks.
Thank you, Dr. Sarkar. A very good evening to all. This is my immense pleasure to deliver vote of thanks on today's webinar on recent advances in renewable energy and materials for sustainable energy future prospect. Under the aegis of Mechanical Engineering Division Board. First of all, I would like to convey my heartfelt gratitude and thanks to Dr. Rangareddy Sham, Chairman, Mechanical Engineering Division Board, IEI, for his resourceful deliberation. Due to some emergency work, Dr. H.O. Thackeray, President IEI, and Dr. G. Ranganath, Chairman CATE, could not join today's webinar. We feel sorry for that. So as our panelist, Dr. Tapas Kumar Saha, Professor Electrical Engineering, NIT Durgapur. He also not joined today's meeting. I am thankful to Mr. Safiqul Islam, Chairman, IEI Durgapur Local Center, for his nice welcome address. I feel gratitude to our learned panelists, Dr. Subhasis Roy, Assistant Professor, Department of Chemical Engineering, University of Calcutta, to deliver his lecture, which is very resourceful to the audience. I also thank to Dr. Apurvo Laik, Professor, Department of Mechanical Engineering, National Institute of Technology, Durgapur, for his excellent and lively deliberation. Special thanks to Dr. Ananto Sarkar, Assistant Professor, Department of Chemical Engineering, NIT Durgapur, who ran today's proceedings nicely as moderator. Last but not the least, I would like to thank Dr. Bimal Das, Assistant Professor, Department of Chemical Engineering, NIT Durgapur, and a committee member of IEI DLC to give us enough support to make the webinar a grand success. Finally, I would like to thank all corporate members and others who attended today's webinar in virtual mode and make this evening's proceeding a grand success. Thank you, sir. Thank you all.
Thank you, sir. Sir, Kingsuk sir. Hello, Kingsuk sir. Hello.
Sir,
Please close the door. Please close the program. It is already over. Kingsuk sir. Hello.
Sir, yes, sir.
Please close the program.
close the
Sir.
proceedings.
Thank you, sir.
Oh, most welcome, and thank you all.